Around 66 million years ago, a rock the size of a mountain came screaming out of the blackness of space. It was traveling at about 45,000 miles per hour, or 20 kilometers per second. It didn't slow down much as it punched through Earth's atmosphere. The destination was a shallow sea where the Yucatan Peninsula is today. The impact released energy equivalent to billions of atomic bombs. It gouged a crater 150 kilometers wide and 20 kilometers deep. The initial blast incinerated everything for 1,000 kilometers in every direction. It triggered a global earthquake that may have lasted for weeks. It sent a tsunami hundreds of meters high racing across the oceans. But that was just the start. The real killer was the aftermath. Pulverized rock and soot were thrown into the high atmosphere, blanketing the entire planet. The sun was blotted out, photosynthesis stopped, plants died, the food chain collapsed from the bottom up. The planet plunged into a long, dark winter. When the dust finally settled, more than 75% of all species on Earth were gone. The dinosaurs, after ruling for 150 million years, were history. One rock from space did that. It was a demonstration. The universe is not a safe, nurturing place. It is a vast, chaotic machine full of forces that can erase life in an instant. The Chicxulub impact was not a freak accident. It was just a turn of the wheel. There are many other ways the universe is actively trying to kill us. Some are loud and fast. Others are silent and slow. But they are all built into the fundamental laws of physics and the structure of the cosmos. Our existence is a temporary lucky streak in a very dangerous game. Number 20, the rocks are falling. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters wide. It never hit the ground. Yet the shockwave from its atmospheric explosion injured over 1,500 people. The 1908 Tunguska event, likely a similar airburst from an object 50 to 60 meters wide, flattened over 2,000 square kilometers of Siberian forest. NASA estimates it has only located about 40% of the near-Earth asteroids that are 140 meters or larger, the size considered a city killer. The most famous threat is the most straightforward. An asteroid or a comet hits Earth. We have a very clear record of this happening. The dinosaur killer was the big one, but it was not the only one. Earth's surface is littered with impact craters, though most have been erased by weather and geology over millions of years. The moon, with no atmosphere or weather, shows the true history of our neighborhood. It is covered in scars. We are in a cosmic shooting gallery. The objects that threaten us are leftovers from the formation of the solar system about 4.6 billion years ago. Most of them are in the asteroid belt between Mars and Jupiter, but Jupiter's immense gravity can nudge these rocks out of their stable orbits. Some get flung out of the solar system entirely, others get sent on a path that crosses Earth's orbit. These are the ones we worry about. They are called near-Earth objects, or NEOs. A small impact like Chelyabinsk is a local disaster. It breaks windows, causes injuries from flying glass, and creates a panic. A slightly larger one, like Tunguska, can wipe a major city off the map. An object a few hundred meters across would devastate an entire state or a small country. The initial blast would be followed by earthquakes and, if it hit the ocean, a massive tsunami. But the real problem comes from objects 1 kilometer or larger. An impactor of this size wouldn't just be a regional disaster. So, it would be a global one. The impact would throw enormous amounts of dust and soot into the stratosphere. This material would spread around the world, blocking sunlight. This is the impact winter. And temperatures would plummet, crops would fail worldwide, the entire global food supply would collapse, leading to mass starvation. This is how a single rock can kill billions of people who are thousands of miles away from the impact itself. Scientists are working on this problem. Programs like NASA's Planetary Defense Coordination Office track NEOs. They use telescopes on the ground and in space to find and plot the orbits of potentially hazardous asteroids. The goal is to find them decades or even centuries before they might hit us. If we have enough warning, we can do something about it. The DART mission, the Double Asteroid Redirection Test, was a proof of concept. In 2022, NASA intentionally crashed a spacecraft into a small asteroid named Dimorphos. The goal was not to destroy it, but to nudge it. A tiny change in an asteroid's velocity applied years in advance is enough to make it miss Earth entirely. The mission was a success. It showed that we have the technology to defend ourselves. But it only works if we see the threat coming. The universe has a lot of rocks, and we haven't found them all. The sky is big, and some objects are very dark and hard to see. They come from all directions, and all it takes is one. Number 19, the silent flash from deep space. A single gamma ray burst can release more energy in 10 seconds than our sun will in its entire 10 billion year lifetime. If a GRB went off in our own galaxy and was pointed directly at us, it could strip away half of our planet's ozone layer in a matter of seconds. Such an event is estimated to occur on a timescale of a few 100 million years. A nearby star system, WR-104, about 7,500 light-years away, is a candidate for producing a future GRB, and its rotational axis might be pointed close to our direction. Gamma-ray bursts, or GRBs, are the most powerful explosions in the universe. They are flashes of high-energy light that come from distant galaxies. For a long time, we didn't know what caused them. They were first detected in the 1960s by military satellites looking for secret nuclear tests. The flashes were random, coming from all over the sky, and they were incredibly brief, lasting from a few milliseconds to a few minutes. We now know there are two main types. Long-duration GRBs lasting more than 2 seconds are thought to be caused by the collapse of massive, rapidly spinning stars into black holes. These are called hypernovas. As the star's core collapses, it shoots out jets of plasma at nearly the speed of light. If one of these jets is pointed at Earth, we see a gamma ray burst, and short-duration GRBs are believed to be caused by the merger of two neutron stars, or a neutron star and a black hole. The danger from a GRB is not from a direct blast of heat or energy like an asteroid impact. The threat is more subtle and insidious. Gamma rays are a form of light, but they are extremely high energy. If a powerful GRB were to occur within our own Milky Way galaxy, and its beam hit Earth, the gamma rays would interact with our atmosphere. They wouldn't reach the ground, but they would trigger a series of chemical reactions in the upper atmosphere. The primary effect would be the destruction of the ozone layer. The gamma rays would break apart nitrogen and oxygen molecules. These would then react with ozone, destroying it. Our ozone layer is what protects life on the surface from the sun's harmful ultraviolet radiation. Without it, or with a severely depleted version of it, UV levels would skyrocket. This would be devastating for life. It would cause a massive increase in skin cancer and cataracts in animals. But the bigger problem would be for the base of the food chain. Plankton in the oceans, which produce a huge amount of our oxygen, are very sensitive to UV radiation. Increased UV would kill them off in massive numbers. Crops on land would also be severely damaged. The entire global ecosystem would be thrown into chaos. Like, we would not see it coming. The gamma rays travel at the speed of light. The first we would know of it would be the flash of light in the sky, followed by the silent, invisible destruction of our protective shield. There is no defense against it. You cannot nudge a beam of light. You cannot build a shield for an entire planet. The odds of a GRB hitting us are low. Most of them happen in very distant galaxies billions of light years away. For one to be a threat, it would need to happen in our own galaxy and be pointed directly at us. The beams are narrow, like a laser pointer, so even if a nearby star goes hypernova, the jet would most likely miss us. But The universe is old and time is long. Geologists have found evidence in the fossil record of past mass extinctions that might line up with this scenario. The Ordovician-Silurian extinction event about 450 million years ago has some characteristics that could be explained by a nearby GRB. It's a low probability, high consequence event, a silent killer from across the galaxy. Number 18, the neighborhood bomb. The blast wave from a supernova can travel at up to 10% the speed of light. The star Betelgeuse, a red supergiant in the constellation Orion, is only 640 light-years away and is expected to go supernova sometime in the next 100,000 years. If a supernova were to occur within 25 light-years of Earth, it would likely cause a mass extinction event. A supernova is the explosive death of a star. It happens in two main ways. A massive star, much bigger than our sun, runs out of nuclear fuel. Gravity wins the battle, and the star's core collapses catastrophically. The collapse triggers a massive explosion that blasts the star's outer layers into space. The other type involves a white dwarf, the dead remnant of a smaller star like our sun. If a white dwarf is in a binary system with another star, it can steal material from its companion. When it gets heavy enough, it triggers a runaway thermonuclear explosion, and the whole star is obliterated. A supernova is one of the most spectacular events in the cosmos. For a few weeks, a single exploding star can outshine its entire galaxy. The explosion creates and scatters heavy elements like iron, gold, and uranium into space. These elements are necessary for making planets like Earth and life like us. We are, in a very real sense, made of star stuff from ancient supernovae. But you don't want to be too close to one when it goes off. A supernova releases a flood of deadly radiation. Gamma rays, X-rays, and high-energy particles would wash over our solar system. The effects would be similar to a gamma ray burst, but potentially more prolonged. The radiation would shred our ozone layer, exposing the surface to deadly UV radiation from our own sun. There is also a physical blast wave. The expanding cloud of gas and dust from the supernova, called a supernova remnant, travels outwards at incredible speeds. If we were close enough, this wave would eventually reach our solar system. It could disrupt the Oort cloud, the vast cloud of comets at the edge of our solar system, sending a shower of them towards the inner planets, including Earth. It could even compress our sun's protective magnetic bubble, the heliosphere, exposing us to more harmful cosmic rays from the galaxy. The safe distance is thought to be about 25 to 50 light years. Any closer, and the effects on the atmosphere and life would be severe. We don't know of any stars that close that are about to go supernova right now. But a star's distance can be hard to measure, and our understanding of stellar evolution isn't perfect. There is evidence that Earth has been hit by the fallout from nearby supernovae in the past. Scientists have found a specific radioactive isotope of iron, iron-60, in deep-sea crusts and even in lunar samples. And iron-60 is produced in supernovae. Its half-life is about 2.6 million years, which is short in cosmic terms. This means that any iron-60 found on Earth must have come from a relatively recent nearby explosion. The deposits suggest one or more supernovae went off near our solar system a few million years ago. This coincides with a period of climate change and some extinctions on Earth. It wasn't a mass extinction, but it shows that we are not isolated from the violence of the galaxy. Our neighborhood has its dangers. Betelgeuse will be an amazing sight when it finally explodes. It will be as bright as the full moon, visible during the day. But we're lucky it's a comfortable 640 light years away. If it were 10 times closer, it would be a very different story. Number 17, our star's violent mood swings. A large solar flare can release the energy of 1 billion megatons of TNT. The most powerful solar storm on record, the Carrington event of 1859, caused telegraph systems worldwide to fail, with some operators reporting sparks flying from their equipment. A storm of that magnitude today could cause trillions of dollars in damage and lead to blackouts lasting for months or even years. Our own sun is the most immediate and constant cosmic threat we face. It gives us life, but it also has a violent temper. The sun is a churning ball of hot plasma with powerful magnetic fields. Sometimes these magnetic fields get twisted and tangled. When they snap and reconfigure, they can release enormous amounts of energy in the form of a solar flare or a coronal mass ejection CME. A solar flare is an intense burst of radiation. A CME is a massive bubble of plasma and magnetic field that gets flung out from the sun into space. If a CME is aimed at Earth, it can have serious consequences. We are mostly protected by our planet's magnetic field, the magnetosphere. It acts like a shield deflecting the charged particles from the sun, but a powerful CME can overwhelm this shield. The Carrington event in 1859 was the benchmark. It was caused by a massive CME that hit Earth's magnetosphere head-on. In the 19th century, the only global electronic infrastructure was the telegraph system. It was fried. Auroras, the northern and southern lights, were seen as far south as Cuba and Hawaii. They were so bright that people could read a newspaper by their light at night. If a Carrington-level event happened today, the consequences would be catastrophic. Our modern civilization is completely dependent on electricity and electronics. A powerful CME would induce huge electrical currents in our power grids. Transformers would overheat and melt. This would cause widespread cascading blackouts. It wouldn't just be the lights going out. Without electricity, there would be no clean water pumped to our homes. No refrigeration for food and medicine, no gasoline pumps, no banking, no internet, no communications. It would be a return to a pre-industrial age, but with a population of billions who have no idea how to survive in such a world. The immediate problem would be repairing the grid. Large transformers are custom built and take a long time to make and install. It could take years to get the power back on in some areas. The social and economic collapse that would follow is hard to overstate. And we've had close calls. In July 2012, a massive CME, at least as powerful as the Carrington event, erupted from the sun. It missed Earth. It crossed our orbit when we were on the other side of the sun. If it had happened just 9 days earlier, it would have been a direct hit. We got lucky. The sun goes through an 11-year cycle of activity. During the solar maximum, flares and CMEs are much more common. We are currently in a new solar cycle that is ramping up in activity. Scientists at NOAA's Space Weather Prediction Center monitor the sun 24/7. They can give us a day or two of warning if a big CME is headed our way. This gives power grid operators time to take precautions, like shutting down parts of the grid to prevent them from being overloaded. But for a truly massive storm, it might not be enough. Our star is the source of all life on Earth. But it also has the power to switch off our civilization in a matter of hours. Number 16, the invisible drifter. There could be as many as 100 million stellar mass black holes roaming our Milky Way galaxy alone. These objects are completely dark and only detectable by the way their gravity bends the light of stars behind them, a phenomenon called gravitational microlensing. Say a rogue black hole passing through our solar system, even at a great distance, could gravitationally disrupt the orbits of the planets, potentially flinging Earth into a much colder or hotter orbit, or out of the solar system entirely. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. We usually think of them as being stationary, like the supermassive one at the center of our galaxy. But not all black holes stay put. When a massive star dies in a supernova, the explosion is not always perfectly symmetrical. If the explosion is lopsided, the newly formed black hole can be kicked out into space at high speed like a cannonball. These are rogue black holes. They wander the galaxy untethered to any star system. They are the ultimate stealth killers. They emit no light. They are invisible. The only way to detect them is indirectly, by their gravitational influence on things around them. If a rogue black hole were to pass through our solar system, we would not see it coming. The consequences would depend on how close it got. A direct hit is almost impossible. Space is mostly empty. But it wouldn't need to hit us. Its immense gravity would be the weapon. If a stellar mass black hole, one with the mass of a few suns, passed through the outer solar system, it could wreak havoc. It could tug on the orbits of Neptune and Uranus. It could disrupt the Oort cloud, sending a deadly rain of comets toward Earth, a bombardment that could last for millions of years. If it passed closer through the inner solar system, the effects would be more direct and immediate. It could change the shape of Earth's orbit. It could make our orbit more elliptical. This would cause extreme temperature swings, with scorching hot summers and freezing cold winters, making the planet uninhabitable. It could pull Earth into a new orbit, either closer to the sun, where we would burn up, or further away, where we would freeze. In the worst case scenario, it could gravitationally eject Earth from the solar system altogether. Our planet would become a cold, dark orphan world, drifting alone in the interstellar void. The probability of this happening is extremely low. The galaxy is vast, and the chances of a random encounter are tiny, but it's not zero. In 2022, astronomers used the Hubble Space Telescope to confirm the existence and measure the mass of a rogue black hole for the first time. They found it by watching how its gravity bent the light of a background star. It has a mass of about 7 times our Sun and is traveling at 100,000 miles per hour. It's about 5,000 light years away, so it's no threat, but its discovery proves that these invisible wanderers are out there. They are a silent, dark component of our galaxy, a cosmic ghost that could appear without warning. Number 15, the unlit bowling ball. Astronomers estimate there could be more rogue planets not orbiting any star than there are stars in the Milky Way. In 2021, a team of scientists found evidence for a new population of Earth-sized free-floating planets, suggesting there could be billions of them in our galaxy. A rogue planet passing through our solar system would not be as destructive as a black hole, but it could still cause significant orbital disruptions and potentially eject Earth. It's just like black holes, planets can be ejected from their home star systems. During the chaotic early days of a solar system's formation, gravitational interactions between large planets can be unstable. Sometimes one of the planets loses the gravitational tug of war and gets flung out into interstellar space. These are rogue planets, or free-floating planets. They are incredibly difficult to detect. They don't produce their own light. They are much smaller and less massive than stars or black holes. Like rogue black holes, they are usually found through gravitational microlensing, the brief brightening of a background star as the rogue planet's gravity focuses its light. We have found dozens of them this way, but they are likely just the tip of the iceberg. The galaxy could be teeming with these dark, cold worlds. The threat from a rogue planet is similar to that of a rogue black hole, just on a smaller scale. A Jupiter-sized rogue planet passing through the outer solar system could still disrupt the Oort cloud and send comets our way. If it passed through the inner solar system, it could alter the orbits of the planets. A close pass by an Earth-sized rogue planet could be enough to change our orbit, leading to catastrophic climate change. A larger one could eject us from the solar system. There's another, stranger possibility. A large rogue planet could be captured by our sun's gravity. It would settle into a new, probably highly elliptical orbit. This new neighbor would create gravitational chaos. It would tug on all the other planets, including Earth, making the entire solar system unstable. Stable orbits that have existed for billions of years could be thrown into disarray. The chances of any single rogue planet hitting our solar system are minuscule, but if there are truly billions or even trillions of them wandering the galaxy, the cumulative probability over geological timescales becomes something to consider. They are like unlit bowling balls rolling around in a dark room. Most of them will miss us. But we don't know where they all are or how many there are. The discovery of each new one is a reminder that the space between the stars is not empty. It's filled with dark, unseen objects, products of cosmic violence from long ago. Number 14, when galaxies collide. The Andromeda Galaxy is currently moving towards our Milky Way galaxy at a speed of about 110 kilometers per second, or 250,000 miles per hour. The two galaxies are predicted to collide and merge in about 4.5 billion years. While direct star collisions will be rare, the gravitational upheaval will likely fling our solar system into a completely different region of the new, larger galaxy. Galaxies are not static islands of stars. They move and they interact. Our own Milky Way is part of a group of galaxies called the Local Group. The other big player in this group is the Andromeda Galaxy, and it's heading right for us. This is not speculation. We have measured its velocity using the Doppler shift of its light. The collision is inevitable. When the two galaxies collide, it won't be like two solid objects crashing into each other. Our galaxies are mostly empty space. The stars themselves are very unlikely to hit each other. The average distance between stars is huge, but the gravitational interaction will be immense. The two giant spiral galaxies will pull and tear at each other over hundreds of millions of years. Their beautiful spiral structures will be destroyed, and they will eventually merge into a single, larger, blob-shaped galaxy, which some astronomers have nicknamed Milkomeda. The fate of our solar system in this merger is uncertain. It's very unlikely we will be destroyed, but we will almost certainly be moved. Computer simulations show that our solar system could be thrown far out into the halo of the new galaxy, a region with very few stars, or we could be sent plunging towards the new, chaotic galactic center. The galactic center is a dangerous place. It is home to a supermassive black hole. The merger will funnel huge amounts of gas and dust towards the center, feeding the black holes of both galaxies. This will ignite a quasar, a blazingly bright object powered by matter falling into a black hole. The radiation from this newly active galactic nucleus could be intense. If we end up too close, it could be a problem for any life that might still exist on Earth. The biggest change will be the night sky. As Andromeda gets closer, it will grow larger and larger in the sky. For millions of years leading up to the merger, it will be a spectacular, terrifying sight. Then, as the galaxies begin to interpenetrate, our familiar constellations will be gone. The sky will be filled with new stars, streams of gas, and bright regions of new star formation triggered by the collision. This is a very long-term threat. It's billions of years away. By that time, our sun will be entering its red giant phase and will have already made Earth uninhabitable. But it is a fundamental part of our future. Our quiet galactic neighborhood is temporary. We live in a dynamic universe, and we are on a collision course. The very structure of our home is destined to be ripped apart and reassembled into something new and unrecognizable. Number 13, the enemy within. The last super eruption on Earth was the Toba eruption in Indonesia about 74,000 years ago. It ejected an estimated 2,800 cubic kilometers of material and may have plunged the planet into a volcanic winter that lasted for years, possibly reducing the entire human population to just a few thousand individuals. The Yellowstone caldera in the United States has had 3 major eruptions in the last 2.1 million years, and it is still an active system with the ground above its magma chamber rising and falling. Not all threats come from outer space. Some of the most devastating are right under our feet. A supervolcano is not a typical cone-shaped mountain. It is a massive caldera, a huge depression in the ground left over from a previous eruption of unimaginable scale. These eruptions are thousands of times larger than any volcanic eruption in recorded history. When a supervolcano erupts, it doesn't just produce lava, it blasts a colossal amount of ash, dust, and sulfur dioxide into the stratosphere. The immediate area for hundreds of kilometers would be buried in hot ash, killing everything. But like a major asteroid impact, the global consequences are the most severe. The sheer volume of material injected into the atmosphere would block sunlight, creating a volcanic winter. Global temperatures would drop significantly. This would lead to widespread crop failures and famine. The sulfur dioxide would mix with water in the atmosphere to form sulfuric acid, which would fall as acid rain, poisoning water supplies and soil. The Toba eruption is a chilling example. Genetic evidence suggests that the human population went through a severe bottleneck around that time. We almost didn't make it. A single volcano nearly wiped out our entire species. There are about 20 known supervolcanoes on Earth. One of the most famous is Yellowstone. Beneath the beautiful national park lies a giant magma chamber. Yellowstone has a history of massive eruptions. The last one was 640,000 years ago. Geologists say it is not due for an eruption, as these events are not on a fixed schedule. The probability of a Yellowstone super eruption in any given year is very low, about 1 in 730,000. But low probability does not mean no probability. The effects of a Yellowstone eruption would be a continental scale disaster for North America. A huge part of the United States would be covered in a thick layer of ash. The ash is made of tiny shards of rock and glass. It would destroy buildings, contaminate water, and be lethal to breathe. Agriculture in the American Midwest, the world's breadbasket, would be wiped out for years. The global effects on climate would be severe, leading to a worldwide food crisis. We monitor these systems closely. Scientists use seismometers to detect ground tremors, GPS to measure ground deformation, and analyze gases being released from the ground. We would likely have some warning, perhaps weeks or months, that an eruption was becoming more likely, but there is nothing we can do to stop it. We are living on a planet with a hot, violent interior. We are just passengers on a thin crust floating on a sea of molten rock, and that molten rock finds a way out. Number 12, losing our planetary shield. Earth's magnetic field has weakened by about 9% over the last 200 years. The last full magnetic reversal was the Brunhes-Matuyama reversal about 780,000 years ago. During a reversal, the main dipole field weakens significantly, and multiple temporary magnetic poles can pop up all over the planet. This process can take several thousand years to complete. Earth is a giant magnet. Its core of molten iron acts like a dynamo, generating a powerful magnetic field that extends far out into space. This magnetosphere is our primary shield against harmful radiation from the sun and from deep space. It deflects the solar wind, a constant stream of charged particles from the sun. It also protects us from cosmic rays, high-energy particles from distant supernovae. Without it, our atmosphere would be slowly stripped away into space, just as happened on Mars after its magnetic field died. But our magnetic field is not stable, it fluctuates in strength and direction, and every few 100,000 years on average, it completely flips. The North Magnetic Pole becomes the South Magnetic Pole, and vice versa. We know this from studying the magnetic orientation of ancient rocks. When lava cools, magnetic minerals within it align with the Earth's field at that time, creating a permanent record. This geological record shows hundreds of reversals throughout Earth's history. We are currently in a period where the field is weakening. This might be a sign that we are heading towards another reversal. During the reversal process, the main field doesn't just disappear and reappear in the opposite direction. It becomes much weaker and more complex. Instead of a simple north and south pole, we could have multiple smaller poles all over the planet. The whole process could take thousands of years. During this transition period, our shield would be down. With a much weaker magnetic field, more radiation would reach the planet's surface and atmosphere. This would have several dangerous effects. It would increase the risk for life on the surface from cosmic rays, which can damage DNA. It would pose a serious health risk to airline passengers and astronauts. The biggest impact would be on our technology. The satellites in orbit would be much more vulnerable to damage from charged particles. This would threaten our global communications, GPS navigation, and weather forecasting systems. The increased radiation would also induce currents in our power grids, similar to a solar storm, potentially causing widespread blackouts. The atmosphere itself would be more exposed to the solar wind. This could lead to increased atmospheric loss to space over long periods. It might also affect the climate, although the exact mechanisms are not well understood. We cannot stop a magnetic field reversal. It is a fundamental process of our planet's geology. The last one happened 780,000 years ago. Humans were around then, and our ancestors clearly survived it. But they didn't have a global civilization dependent on fragile electronics. For us, losing our planetary shield, even temporarily, would be a much more serious crisis. Number 11. The constant rain of damaging particles. Cosmic rays are not rays. They are high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. A single one of the most energetic cosmic rays ever detected, the Oh My God particle in 1991, had the kinetic energy of a baseball traveling at 60 miles per hour, all packed into a single subatomic particle. These particles constantly bombard Earth's atmosphere from all directions. The universe is filled with a constant, invisible rain of high-energy particles. These are galactic cosmic rays. They are born in the most violent events in the cosmos, like supernovae. So they are accelerated to incredible speeds as they travel through the magnetic fields of the galaxy. They bombard our solar system from all directions all the time. Earth's atmosphere and magnetic field protect us from most of them. When a cosmic ray hits the upper atmosphere, it collides with an air molecule, creating a shower of secondary particles that rain down to the surface. We are being hit by these secondary particles all the time. They are a source of natural background radiation. This constant radiation has an effect on life. It can cause genetic mutations. Some scientists believe that cosmic rays are a driver of evolution, creating the random mutations upon which natural selection acts. But they also cause damage. They are a known cause of cancer. At sea level, the dose is low. But if you are a frequent flyer, you receive a higher dose because there is less atmosphere above you to protect you. Astronauts in space are at the highest risk. Protecting them from cosmic rays is one of the biggest challenges for long-duration space missions, like a trip to Mars. The cosmic ray threat can also change over time. If the sun's magnetic field weakens, or if our own planet's magnetic field weakens during a reversal, more cosmic rays can reach Earth. A nearby supernova would also temporarily flood our solar system with a much higher flux of these particles. There is also a technological threat. Cosmic rays can flip bits in computer memory. A high-energy particle can pass through a microchip and change a 0 to a 1, or a 1 to a 0. This is called a single event upset. For your home computer, it might just cause a crash that you fix by rebooting. But for critical systems like airplanes, medical equipment, or power grids, a single bit flip can have disastrous consequences. The engineers have to design radiation-hardened electronics for these applications, but the threat is always there. We are living in a sea of radiation. It's a fundamental part of our environment. It may have helped to create the diversity of life on Earth, but it is also constantly causing damage at a microscopic level. It is a slow, persistent, and inescapable threat from the universe. Number 10. The ultimate off switch. The standard model of particle physics suggests that the vacuum of our universe may not be in its true lowest energy state. It might be in a false vacuum. If a small region of the universe were to tunnel into the true vacuum state, it would create a bubble of true vacuum that would expand at the speed of light, destroying everything in its path. The laws of physics, as we know them, would cease to exist inside the bubble. This is perhaps the most terrifying threat of all, because it is built into the fundamental nature of reality itself. It's called vacuum decay or vacuum metastability event. To understand it, think of the state of the universe like a ball in a landscape of hills and valleys. The universe wants to be in the lowest possible valley, the state of lowest energy. We assume we are in the lowest valley, the true vacuum, but what if we are not? What if we are in a smaller, shallower valley, a false vacuum? There could be a much deeper valley nearby, the true vacuum. Quantum physics allows for something called quantum tunneling. The ball representing the state of the universe could spontaneously tunnel through the hill separating the two valleys. If this happened somewhere, anywhere in the universe, it would be the beginning of the end. A bubble of the true vacuum would form. Inside this bubble, the fundamental constants of nature would be different. The properties of elementary particles like electrons and quarks would change. The forces that hold atoms together might be different or might not exist at all. It would be a completely different reality. You know, this bubble would expand outwards in all directions at the speed of light. As the wall of the bubble passed over Earth, it would be instant annihilation. Atoms would be ripped apart. Stars, planets, and galaxies would be erased. The very laws of physics that allow our existence would be replaced. We would have no warning. Since the bubble expands at the speed of light, we could not see it coming. One moment, the universe is as it is. The next, it is gone, replaced by a new set of physical laws in which we cannot exist. Is this a real threat? According to our best understanding of physics, particularly the properties of the Higgs boson, it is a possibility. The calculations depend on the precise masses of fundamental particles. Current measurements suggest that our universe is either stable or very, very close to the line of being metastable. If it is metastable, it means that a false vacuum decay could happen, but the lifetime of our current vacuum is predicted to be incredibly long, trillions upon trillions of years, far longer than the current age of the universe. But these calculations have uncertainties. A new discovery in particle physics could change the picture. And even if the chance is tiny, the event is the ultimate catastrophe. It is the universe turning itself off. It is not an external object or a burst of energy. It is the very fabric of reality rewriting itself and, erasing us in the process. Number 9, the slow fade to nothing. The second law of thermodynamics states that the total entropy, or disorder, of a closed system always increases over time. The universe is thought to be a closed system. This means that eventually all the available energy in the cosmos will be evenly distributed and no more useful work will be possible. This final state is known as the heat death of the universe. This threat is not sudden or violent. It is the slowest, most inexorable fate imaginable. It is the ultimate consequence of the laws of thermodynamics. The universe began in a very hot, dense, low entropy state, the Big Bang. Since then, it has been expanding, cooling, and becoming more disordered. The process will take an unimaginably long time. First, in about 100 trillion years, all star formation will cease. The gas needed to make new stars will be used up. The universe will become darker, filled only with long-lived red dwarf stars, and the dead remnants of larger stars, white dwarfs, neutron stars, and black holes. Over even longer timescales, the planets will be stripped from their dead stars and wander the dark void. The dead stars themselves will eventually radiate away their heat and fade to black. The galaxies will dissolve as their stellar remnants are flung out into intergalactic space through gravitational encounters. The universe will then be a thin, cold soup of black holes, dead stars, and subatomic particles. But the process is not over. Stephen Hawking showed that black holes are not completely black. They slowly evaporate through a process called Hawking radiation over stupendous timescales. Even the supermassive black holes at the centers of galaxies will evaporate away into a bath of low-energy photons. Finally, after a time so long it defies human comprehension, perhaps 10 to the power of 100 years, the universe will approach a final state of maximum entropy. It will be a vast, cold, dark, and empty void with particles and low-energy radiation distributed almost perfectly uniformly. In this state, There will be no temperature differences, no energy gradients, nothing can happen. No work can be done, no information can be processed, no life in any form we can conceive of can exist. Time itself will lose its meaning. This is the heat death. It is not an attack. It is simply the universe running down like a clock winding down to a final permanent stop. It is the ultimate triumph of decay and disorder. Every structure, from stars to atoms themselves, is temporary. The final state of the universe is a featureless, eternal nothingness. Number 8, the universe tears itself apart. Current observations show that the expansion of the universe is accelerating. This acceleration is driven by a mysterious force called dark energy. If dark energy is a phantom energy whose density increases over time, the expansion will become so powerful that it will eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms in an event called the Big Rip. The discovery that the expansion of the universe is accelerating was a shock to physicists. It implies that there is some kind of repulsive force or energy inherent in space itself. We call it dark energy, but, we don't know what it is. Its future behavior will determine the ultimate fate of the universe. One possibility is the Big Rip. This scenario assumes that dark energy is not a constant, but a form of phantom energy that grows stronger over time. As the density of dark energy increases, its repulsive force will become more and more dominant. At first, it would pull apart clusters of galaxies. Then, as the expansion becomes even more powerful, it would overcome the gravity holding individual galaxies together. The Milky Way would be torn apart. As the end approaches, the pace of destruction would quicken dramatically. In the final stages, the gravitational pull holding our solar system together would be overwhelmed. The planets would be flung away from the sun. Then the force would be strong enough to overcome the gravity holding the Earth itself together. The planet would be ripped into its constituent pieces. In the last few minutes, the electromagnetic force holding atoms and molecules together would fail. All matter would be dissociated into its fundamental particles. Finally, in the last fraction of a second, the strong nuclear force would be overcome, and the atomic nuclei themselves would be torn apart. Space-time itself would be ripped asunder. This is a very different end from the slow, cold heat death. And, it is a violent, finite end. All structures at all scales are destroyed in a final cataclysmic moment. Whether the Big Rip will happen depends on the nature of dark energy, which is one of the biggest mysteries in modern physics. Current measurements are consistent with a constant dark energy, which would lead to a heat death scenario. But the measurements have uncertainties. The phantom energy scenario of the Big Rip is still a possibility. If it is our fate, then the universe is not just trying to kill us, it is planning to annihilate the very fabric of existence itself. Number 7. Our star's inevitable demise. The sun is about 4.6 billion years old, roughly halfway through its stable hydrogen burning phase. In about 5 billion years, it will run out of hydrogen in its core and begin to evolve into a red giant. As it expands, its outer layers will swell to engulf the orbits of Mercury, Venus, and possibly Earth. Even if Earth is not swallowed, the intense heat from the bloated sun will boil away our oceans and strip away our atmosphere, rendering the planet a scorched, lifeless rock. This is not a matter of probability, it is a certainty. All stars have a life cycle, and our sun's end is preordained. It is currently in its main sequence phase, a long, stable period where it fuses hydrogen into helium in its core. This process provides the energy that supports life on Earth. But the hydrogen fuel in the core is finite. When it runs out, the sun's structure will change dramatically. The core will contract and heat up. This will cause the outer layers of the sun to expand enormously. The sun will become a red giant. Its surface will cool, making it appear red, but its total energy output will be much greater. Its radius will swell to about 250 times its current size, it will definitely swallow Mercury and Venus. Earth's fate is on the borderline. Some models predict we will be engulfed. Others suggest that the sun will lose some mass as it expands, which will cause Earth's orbit to move outwards, allowing us to just escape being swallowed. But it doesn't matter. Escaping the sun's grasp would be a hollow victory. As the red giant sun fills our sky, its intense heat will be more than enough to destroy all life. The surface temperature on Earth will rise to over 1,000 degrees Celsius. The oceans will boil away. The atmosphere will be blasted off into space. The rock of the planet itself might begin to melt. Earth will be sterilized. After its red giant phase, the sun will shed its outer layers, creating a beautiful planetary nebula. The core will be left behind as a white dwarf, a hot, dense remnant about the size of Earth. It will no longer produce energy through fusion. It will just be a cooling stellar ember, slowly radiating its remaining heat into space over trillions of years. The death of our sun is the ultimate deadline for any life in this solar system. Long before the red giant phase, the sun's slow increase in brightness will make Earth uninhabitable. In about 1 billion years, the sun will be about 10% brighter than it is today. This will be enough to trigger a runaway greenhouse effect, boiling the oceans and ending life as we know it. Our window of habitability on this planet is not infinite. Our star, the source of our life, will also be the cause of our end. Number 6, the universe's most powerful magnets. Magnetars are a type of neutron star with an incredibly powerful magnetic field, 1,000 trillion times stronger than Earth's. A sudden starquake on the surface of a magnetar can release a giant flare of gamma rays and X-rays. On December 27, 2004, a giant flare from magnetar SGR 1806-20, located 50,000 light-years away, hit Earth. The burst of radiation was so powerful it partially ionized our upper atmosphere and was detected by numerous spacecraft. If this magnetar had been just 10 light-years away, the flare could have caused a mass extinction. Neutron stars are the incredibly dense remnants of massive stars that have gone supernova. They pack the mass of our sun into a sphere only about 20 kilometers in diameter. A magnetar is a special rare type of neutron star with a magnetic field of unimaginable power. The energy stored in this magnetic field is immense. Sometimes the crust of the magnetar can crack under the strain of the magnetic field, a starquake. This event can cause the magnetic field to reconfigure, releasing a huge amount of energy in a giant flare. These flares are similar to solar flares, but on a vastly more powerful scale. The 2004 flare from SGR 1806-20 is a perfect example. Despite being 50,000 light-years away, on the other side of the galaxy, the initial pulse of gamma rays saturated the detectors of every satellite in orbit. It was brighter than any other cosmic gamma ray event ever seen. It disturbed Earth's ionosphere, the electrically charged layer of our upper atmosphere. This event was a wake-up call. It demonstrated the incredible power of these objects. If a magnetar flare like that were to happen much closer, say within a few dozen light years, the consequences would be catastrophic. The flood of gamma rays and X-rays would be far more intense than from a typical supernova. It would completely destroy our ozone layer in an instant. The radiation dose at the surface would be lethal. It would be a sterilizing event for the sun-facing side of the planet. We don't know of any magnetars that close to us. But, neutron stars can be hard to find. Some are only visible when their beams of radiation sweep across Earth, which we see as pulsars. It's possible there are undiscovered quiet magnetars lurking closer than we think. And like supernovae or gamma ray bursts, we would have no warning. The radiation travels at the speed of light. The first sign of trouble would be the deadly flash itself. It's another example of the universe's capacity for sudden, overwhelming violence. Number 5, blasts from the dawn of time. Quasars are the intensely bright, active cores of distant young galaxies. They are powered by supermassive black holes feeding on enormous amounts of gas and dust. The most powerful quasars can be trillions of times brighter than our sun, outshining their entire host galaxy. While most quasars are very far away and existed in the early universe, a dormant supermassive black hole, like the one in our own galaxy, could flare up if it were to receive a large influx of new fuel. Quasars, or quasi-stellar objects, are the lighthouses of the early universe. When we look at them, we are looking billions of years into the past. They represent a phase when galaxies were young and full of gas, providing plenty of food for the supermassive black holes at their centers. As matter swirls into the black hole, it heats up and glows with incredible intensity, launching powerful jets of radiation and particles. The quasar era is mostly over. Most large galaxies, including our own, have quieted down. The supermassive black hole at the center of the Milky Way, Sagittarius A, is relatively dormant. And it's not feeding on much material right now, but it could reawaken. The galactic merger with Andromeda in a few billion years will almost certainly provide a feast of gas for the central black hole, turning our galactic center into a quasar. But even smaller events could trigger a flare-up. A large gas cloud or a star cluster wandering too close could be enough to cause Sagittarius A to become active for a period. If our galactic center were to become a powerful active galactic nucleus AGN, it would be bad news for any life in the inner parts of the galaxy. The core would blast out intense radiation, from radio waves to gamma rays. A high-energy jet could form, pointing out from the galactic poles. While Earth is located out in the suburbs of the galaxy, about 26,000 light-years from the center, a powerful enough outburst could still affect us. An increase in high-energy radiation could damage our atmosphere. It's another long-term, low-probability threat, but it highlights the fact that even the heart of our own galaxy is a sleeping giant that could awaken. The universe is not a static, peaceful place. It is an evolving system, and periods of violent activity can return. Number 4, the unstable clockwork. The orbits of the planets in our solar system seem stable, but they are a chaotic system. Over millions and billions of years, tiny gravitational nudges between the planets can add up in unpredictable ways. Long-term simulations show a small but non-zero probability that Mercury's orbit could become highly eccentric and destabilized by Jupiter's gravity, with a 1% chance that it could lead to a collision with Venus or even Earth in the next few billion years. We tend to think of the solar system as a perfect clockwork machine. The planets follow their elliptical paths around the sun with perfect regularity. But this is not quite true. Every planet in the solar system pulls on every other planet. The system is a complex web of gravitational interactions. For short timescales, the orbits are predictable. But over millions and billions of years, the system is chaotic. This means that tiny differences in the initial positions and velocities of the planets can lead to huge, unpredictable differences in their future orbits. It's impossible to predict the exact state of the solar system billions of years from now. Scientists use computer simulations to explore the possibilities. They run thousands of simulations, each with slightly different starting conditions, to see the range of possible outcomes. Most of the time, the solar system remains stable, but in a small percentage of cases, things go wrong. The main troublemaker is Mercury. It's the smallest planet, and its orbit is the most susceptible to being perturbed by the gravity of the gas giant Jupiter. In some simulations, a particular alignment of the planets causes a resonance between Jupiter and Mercury. This pumps energy into Mercury's orbit, making it more and more elliptical. A highly elliptical orbit for Mercury would be a disaster for the inner solar system. It could cross the orbit of Venus. This could lead to a collision between the two planets, or Mercury could be ejected from the solar system. In a worst-case scenario, the destabilized Mercury could be sent on a collision course with Earth. A collision with another planet would be the ultimate extinction event, completely destroying Earth. This is not a high probability event. The chances are small, on the order of 1% over the next 5 billion years, but It is a real possibility that is allowed by the laws of gravity. The stability of our home is not guaranteed. The beautiful clockwork of the heavens has a small but real element of chaos built into it. The cosmic neighborhood is not as safe as it looks. Number 3, the slow squeeze. Earth's orbit and tilt are not fixed. They undergo long, slow, cyclical changes due to the gravitational pull of other planets, primarily Jupiter and Saturn. These cycles, known as Milankovitch cycles, alter the amount and distribution of solar radiation reaching Earth. They are the primary pacemaker of the ice ages, the long periods when large parts of the planet are covered in massive ice sheets. The last glacial maximum was only about 20,000 years ago, and we are currently in a warm interglacial period within a larger ice age. The universe can kill us slowly as well as quickly. The ice ages are a perfect example. They are not caused by any sudden catastrophe, but by the slow, gentle, and predictable changes in Earth's relationship with the sun. There are 3 main Milankovitch cycles. The first is the eccentricity of Earth's orbit, which changes from nearly circular to more elliptical on a cycle of about 100,000 years. The second is the tilt of Earth's axis, or obliquity, which varies between 22.1 and 24.5 degrees on a 41,000-year cycle. The third is the precession or wobble of the axis, which has a period of about 26,000 years. These 3 cycles combine to change the climate over long periods. When the cycles align to reduce the amount of summer sunlight reaching the northern hemisphere, snow and ice from the winter don't completely melt. This white surface reflects more sunlight back into space, which causes more cooling. This feedback loop can, over thousands of years, lead to the growth of massive continental ice sheets. At the peak of the last ice age, ice sheets up to 3 kilometers thick covered most of Canada, the northern United States, and northern Europe. And sea levels were 120 meters lower than they are today. The climate was colder and drier. This is a dramatically different world. We are currently in a warm period between glacial advances, but the underlying cycles are still at work. In the absence of human-induced climate change, Earth would likely be heading towards another ice age over the next few thousand years. This would be a slow-moving disaster. It would render huge parts of the modern world uninhabitable. Cities like Chicago, Boston, London, and Berlin would be under a kilometer of ice. Agriculture would be pushed towards the equator. It would be a massive challenge for human civilization. The very mechanics of our solar system drive a climate cycle that periodically tries to squeeze life on this planet into a much smaller, colder space. Number 2, the gold makers. A kilonova is the explosion that occurs when 2 neutron stars in a binary system spiral into each other and merge. The event is more powerful than a standard nova, but less than a supernova. The 2017 detection of a kilonova GW17817 confirmed that these mergers are the primary source of most of the heavy elements in the universe heavier than iron, including gold, platinum, and uranium. The explosion also produces a short-duration gamma-ray burst and a blast of high-energy particles. For a long time, the origin of the heaviest elements was a mystery. Supernovae can create elements up to iron, and some heavier ones, but they couldn't account for the amount of gold and platinum we see in the universe. The merger of 2 neutron stars was a leading theory, and in 2017 we saw it happen. The LIGO and Virgo gravitational wave observatories detected the ripples in spacetime from 2 neutron stars spiraling together. Telescopes around the world then saw the explosion, the kilonova. The event is incredibly violent. 2 objects with the mass of the sun, compressed into the size of cities, slam into each other at a significant fraction of the speed of light. The merger creates a black hole or a larger neutron star and blasts a huge amount of neutron-rich material out into space. This material then undergoes rapid nuclear reactions, creating the heavy elements. A kilonova is a source of intense radiation. It produces a short gamma ray burst, which, like the ones from collapsing stars, could be dangerous if it were nearby and pointed at us. It also releases a flood of other radiation and high-energy particles. The real danger is the sheer exoticness of the event. It is a collision of some of the densest matter in the universe. The physics involved is extreme. The fact that these events happen is a reminder of the violent processes that are required to create the elements we consider precious. The gold in a wedding ring was forged in the cataclysmic collision of two dead stars. Like supernovae and magnetar flares, a nearby kilonova would be a major threat. The combination of a gamma-ray burst and a flood of radioactive heavy elements expanding into space would be a deadly cocktail. It's another way the universe demonstrates that creation and destruction are two sides of the same coin. The very process that creates valuable elements is also a world-ending explosion. Number 1, the threat we haven't thought of. In 1967, Jocelyn Bell Burnell detected a strange, perfectly regular radio signal from space. For a time, it was half-jokingly labeled LGM-1 for Little Green Men. It turned out to be the first discovery of a pulsar, a rapidly spinning neutron star. This illustrates a key point: the universe is constantly surprising us with new phenomena we didn't know existed. The most dangerous threat may be one we haven't even conceived of yet. This is the ultimate unquantifiable threat, the unknown unknown. Every threat on this list, from asteroids to vacuum decay, is based on our current understanding of science. But our understanding is incomplete. Every few decades we discover something new about the universe that fundamentally changes our perspective. Dark matter and dark energy were complete surprises. Gravitational waves were predicted, but their direct detection opened a brand new way to observe the cosmos. What else is out there that we don't know about? Could there be exotic objects made of strange matter that could convert normal matter on contact? Could there be long-range forces or particles we haven't detected yet that could have biological effects? Is there some form of extraterrestrial life, even if it's just microbial, that could be a pandemic-level threat if it reached Earth via meteorite? This last idea, panspermia, is usually considered in a positive light as a way life could spread. But it has a dark side. Life from another world would have a completely different biochemistry. Our immune systems would have no defense against it. The history of science is a history of being proven wrong and of discovering that the universe is far stranger and more complex than we ever imagined. The biggest danger is our own ignorance. We are like people living in a single valley, having mapped every rock and tree, who have not yet realized that there is a vast, unexplored continent just over the mountain range with unknown weather patterns and predators. The universe has been operating for 13.8 billion years. It has run countless experiments with physics and matter that we can't even dream of. To assume that we have identified all the major ways it could kill us is the height of arrogance. The final, and perhaps greatest, threat is the certainty that the universe has more surprises in store for us. And not all surprises are good ones.